开始。Hi, I'm Nick Hall. Here we are Group 23, and today we are introducing the simulating phase contrast velocity encoding and reconstruction velocity from K-space. Here are my teammates, Yadi Lan and Ricardo Sun. Next slide, please.
Phase contrast MRI or PCMRI is an imaging technique that measures blood flow by encoding velocity into the phase of the MR signal. It's widely used in cardiovascular imaging to quantify the blood flow, detect abnormalities, and assess vessel function. In this project, we simulate a simplified 2D PCMRI system instead of working with full 4D flow MRI, which can be complex and computationally expensive. We focus on a single cross-sectional slice. This lets us zoom in on the fundamental physics behind velocity encoding, how K-space is generated, and how phase differences are converted into commutative flow maps. By stripping away real-world complications, our simulation gives us a clear view of how PCMRI actually works under controlled conditions, which helps build intuition for interpreting real MRI data and understanding common artifacts like lysing or partial volume effects. The clinical PCMRI accuracy depends heavily on parameters like VENC, spatial resolution, and noise. But in real scans, there are many confounding factors, such as motion, turbulence, and background phase, that make it difficult to understand how each parameter individually affects the final velocity map. Our motivation is to create a synthetic environment where we can isolate these effects. With a controlled simulation, we can clearly study how phase encodes velocity, how lysing occurs when VENC is too low, and how noise or undersampling impacts the reconstruction. We also look at partial volume effects, which are a major source of error in flow quantification, especially near vessel boundaries. Ultimately, this simulation helps us build intuition for how PCMRI behaves under ideal and non-ideal conditions, and how different equestrian settings influence quantitative accuracy. This understanding is essential for improving real PCMRI measurements.
As we previously discussed in class, the phase of an RMI signal is extremely sensitive to magnetic field. Usually we try to minimize the phase error, but in the phase contrast MRI, we intend to use this property. Fundamentally, the phase is the time integral of the magnetic field gradient experiencing by a spin, as the equation shows on the top. For a moving spin, like blood position x tau is changing over time due to the signal. To capture this motion, we apply the bipolar gradient, a positive lobby, and followed by a negative lobby. For stationary tissue, the position is constant, so the second lobby perfectly cancels from the first one. The net phase is zero. However, for the moving blood, the position is changing by the time. This prevents the cancellation and leaves a net phase shift. Critically, if we solve the integral mathematically, it's simplified to the linear equation on the bottom. Phase is directly proportional to the velocity. Next slide, please. For the BENG, we have talked about the phase is proportional to velocity. The slope of the linear relationship is determined by the BENG. As the equation shows, BENG x or speed limit, mapping the physical velocity to MRI phase angle, but there's a strict mathematic limitation. Phase is periodic and strict bounds between negative pi to positive pi. If the velocity exceeding the VINC, the scanner and or simulation code will enforce a module operation to wrap the value back into range. This wrapping can cause Addison, which is high positive velocity misinterpreted as the negative flow, create artifact. Next slide, please. Beyond velocity limitation, we also having the partial volume effect challenge. The partial volume effect in clinical MRI is a pixel is not only a zero dimension point, it's a three-dimensional volume called voxel. At the vessel wall, a single voxel often capture a mix of moving blood and the stationary tissue. The mix of moving blood and stationary tissue will have different signals as the picture showing on the right. They should have an average value by then both values. So we use a specific a MATLAB function image resize with the box kernel to fix this problem. A clinical guideline warns that if we have a fewer than 5 to 6 voxels across the vessel, the effect can be dropped dramatically and we will have a bad accuracy. Next slide, please.
Okay, on this slide, I will introduce the phantom used in our PC MRI simulation. We work with a 1 to 8 plus 1 to 8 image grid to and create a circular vessel with a radius 0.5 in normalized coordinates. Inside this vessel, we define a laminar parabolic velocity profile. This means the flow is highest at the bright center and smoothly decreases to the zero at the vessel wall, which matches what we see in the ground truth figure. Outside the vessel, the velocity is set to 0. For the magnitude image, we assign an intensity of 1 inside the vessel and the 0.1 in the background. This simple phantom gives us a clean interpretable test case for validating the PCMRI pipeline. Next slide, please. Moving on the simulation pipeline, this slide outlines the exact processing steps we implemented. First, we generate complex images as defined by the equations here. We create a reference image, I reference, which has magnitude m and 0 phase. We also define the true phase, phi true, which is proportional to the velocity divided by the VNC. This gives us velocity encoded image, I reference true. Next, we transform these images into the frequency domain using a forward 2D FFT. This produces the k-space data for both the reference k-reference and velocity encoded k-vessel signals. In the k-space domain, we then add noise and apply undersampling patterns to simulate realistic data acquisition limits. Following the pipeline down, we perform image reconstruction using the inverse FFT to get back to the image domain. Then, we calculate the phase difference and the velocity estimation. We compute the phase difference phi difference using the angle of complex conjugate product. We then derive the estimated velocity we estimate by scaling the phase difference by VNC factor over pi. Finally, we compute the error matrix, strictly evaluating the accuracy inside the vessel region. Next slide, please. Here we show the reconstruction results under noise-only conditions with no undersampling. The reference and the velocity encoded images share the same magnitude, meaning only the phase carries flow information. Because the true flow phase stays within pi, there is no phase wrapping. The reconstructed phase difference matches the simulated true phase very closely. As a result, the estimated velocity accurately reproduces the ground truth laminar flow profile. Even with small noise added in k-space, the reconstruction quality remains stable and reliable. Next slide, please. In contrast, when the VNC is set too low, the true flow induced phase exceeds pi. This causes phase wrapping in the reconstruction, producing discontinuous in the phase map. Because velocity estimation depends directly on this wrapped phase, the resulting velocity field becomes highly inaccurate. We observe a ring-shaped aliasing pattern instead of smooth laminar flow. Phase wrapping also leads to larger localized errors, and the velocity MSE rises sharply to about 0.387. These results clearly demonstrate that choosing VNC below the maximum flow velocity leads to the severe aliasing and completely unreliable velocity reconstruction. Next slide, please.
In part A, we simulate the single vessels. We define the stenosis geometry because our model follows the conservation of mass. The velocity naturally accelerates as the radius decreases. You can see in the center there's a bright yellow center, and this shows the velocity have naturally accelerate as the radius decreases. And here we capture the correct flow accuracy. In the high resolution scenarios, the error gap between the two methods shows the very minimal error, the difference in difference. In part two, when we use the more vessels and low resolutions, the error gap had been increased dramatically. As you can see, the normal method fails to capture the fine detail of the edge. This can cause the vessel having a broken detail on the edge. Next slide, please.
Our simulation does have limitations. We are using a simplified 2D phantom rather than full 3D or time-resolved flow. The vessel has an ideal laminar profile, so we don't model the turbulence or anatomical complexity. We also ignore the background phase shifts, system imperfections, and the non-ideal behavior or real gradient pulses. Finally, the relationship between velocity and phase is modeled in its ideal mathematical form. Despite these simplifications, the simulation taught us several important lessons. First, the VENC section is critical. When the VENC is too low, phase drags occur, leading to severe velocity aliasing. When VENC is too high, sensitivity to lower the velocities is reduced. Second, the voxel size matters. The larger voxels increases the partial volume effects, which causes underestimated peak velocity and smearing near vessel boundaries. Overall, these insights reinforce how important equestrian parameters are in PCMRI and how even a simplified model can help us understand and predict the real-world imaging artifacts. And here is the references we use in this project. And thanks for listening.